Can you see everything correctly?
Yes,
Yes,
we
I
can see
Perfect.
transparent.
So, of course, I'd like to thank the organizers for the invitation. I'm enjoying the meeting very much. And I'm going to talk about the possibility that quantum gravity might affect our relativistic properties in theories we use right now, something that came to the attention of the community mainly through works some time ago by Jorge, by Nick, by myself, and others. And this led initially to the assumption that in such a scenario, relativistic symmetries would be broken. This is still a possibility, but we later realized that it's also possible to have such effects preserving relativistic invariance, acquiring new laws, and therefore adapting the transformations between observers to the new laws. I'm mainly going to focus on one single effect, which is possible in both of these scenarios, and concerns the possibility of the speed of ultra-relativistic particles acquiring a tiny energy dependence, a dependence suppressed by one or even more powers of the Planck scale, and therefore so small that in laboratory experiments it would go forever unnoticed, basically. However, we realized that instead, if you use astrophysics as a laboratory, particularly gamma ray bursts, these tiny effects could in principle be studied. And my main objective today is to talk about the possible interplay between macroscopic curvature and these Planck scale effects. But in order to set it up, let me offer a quick perspective on some data actually from astrophysics that are now, after nearly 2 decades, allowing us to actually do what was conceived long ago. So first of all, let me adopt, as many others have done, a statistical approach. So let's look for this would be this energy dependence of the speed of ultra-relativistic particle. It would basically reduce itself into a the correlation between the times of arrival of particles and their energy formula that was first proposed by Jacob and Piran traditionally is described as you see at the center of this slide. So we look for this kind of linear relation between some time delays, let's say, and a certain redshift corrected energy of the particles. And the situation is quite has two sides. On one side, there is an intriguing observation. I give you references because in the time allowed, I couldn't explain the whole analysis, but actually focusing on the highest energy photons from gamma ray bursts, we see statistically a rather strong support for the correlation, as you see on this slide, at least qualitatively. Um, Not all photons follow on a precise line, but the correlation is pretty strong considering the kind of the data obtained. This is the encouraging side. On the same slide is one point in particular. There is some others that could also be discussed, but this one is really striking. This one point, however, renders the appeal of this analysis much less strong. This is a data point from a gamma ray burst GRB090510. Is this one with the red arrow? I point to the one photon which on the previous slide I circled in red. Here I'm showing it instead together with its fellow photons from the same gamma ray burst of highest energy. And you see that this highest energy photon of about 30 GeV comes just at the time when the signal in the range of 1 to 5 GeV is busiest. So it would be, it's not only that it doesn't follow the correlation path, let's say, of other photons in my previous draft, but it doesn't follow in some kind of an apparently irreparable manner, because you would have to, in order to claim that this photon was affected by an effect of in vacuum dispersion as big as suggested by the correlation on the previous, usually doesn't take you to interesting results. So there are really two sides. Overall, this has been, by some authors, underestimated. Overall, the statistical significance is quite impressive, but then on single events, you get a completely different indication from what the statistical analysis suggests. This is and this is, first of all, let me stress, in the old days, indeed, with Jorge, with Nick and others, we were advocating for the birth of the quantum gravity phenomenology. The very fact that I'm analyzing this data in this fashion shows you that quantum gravity phenomenology is being done. Not that we are discovering anything, but surely we have the sensitivity in this analysis for actually doing these studies. And my living review will give you a much broader picture of the field. But for the purposes of my presentation today, really, the facts I just illustrated are the background for understanding our motivation in a very recent study for looking for a different model of this kind of in-vacuum dispersion effects, these effects of energy dependence of the speed of ultra-relativistic particles. Experimentally, there is this data situation which is on one side intriguing and on one other side discouraging. On the theory side, what has happened in the last 20 years is that many more results have suggested that actually these kind of departures from standard relativistic properties might be triggered by macroscopic curvature. In the first models, these effects were modeled assuming that they would be present just as much in the flat spacetime limit. But the recent literature, and again, that would require a dedicated talk, but the recent literature suggests that instead this departure from standard relativistic properties in the quantum gravity realm are triggered by the presence of macroscopic curvature. And this has been known already for several years. The reason why nobody had done phenomenological analysis with this kind of possibility is due basically to the fact that it was expected that it would be hopeless. Because if you go forward and study effects which are Planck scale induced and curvature induced, this means that the smallness of the effect is both caused by the smallness of the Planck length and also by the smallness of curvature. This was the standard folklore that discouraged studies of these models so far. But in light of the situation, we went on and recently studied this possibility. We basically, the first thing that we noticed is actually the argument that the effect when curvature triggers the in-vacuum dispersion would be much smaller is simply incorrect. Curvature is a dimensionful scale in the analysis, and it happens to be the case, and it's not surprising if you think about it, that each time you get the power of curvature, you also get a power of distance. And the distances involved are huge. So actually, it works out in a kind of a mystical way that for every price paid by the smallness of curvature, you get an equally strong benefit from the distance. This triggers off, this perfect balance happens to be present when redshift is about 2 or 2.5, which is actually where most gamma ray bursts are observed. So we immediately noticed that this folklore about curvature triggered effect was incorrect. And we then went on to model, get a toy model of literally the literature on detailed model is rather poor so far. Again, because nobody thought it would matter for phenomenology. But we constructed a toy model. We basically took the standard model which is used in this phenomenology with this redshift dependence formula, which is first in a paper by Jacob and Piran, and we just added an extra term in such a way that there is a cancellation and the effects go away in the flat space-time limit. So we have a toy model where the effects are only present when there is macroscopic curvature. And I will not take the time to describe these formulas in detail. They're simple formulas and they are in this paper which we recently announced. But you can see basically these are formulas in this slide that compare the standard Jacob-Piran scenario and the new scenario we are proposing with curvature triggered effect. And you see that the redshift dependence is just about the same strength. There is no real suppression due to the role of curvature for triggering the effects. The only difference, if you then look more carefully at this formula, is that, as I anticipated, at small redshift, there is a difference. At small redshift, the curvature triggered effects are weaker because you're getting penalized by the smallness of curvature, but you don't get enough premium by the distance. So at small redshift, the new model predicts smaller effects, but at typical redshift of 2 or 3, the model predicts a different formula, but of just the same magnitude, order of magnitude, as the standard phenomenology. And this is basically my key point then for the data analysis, which I showed earlier. On the left, I'm just showing in a different way exactly the same observation of that previous slide I had. So this is the phenomenological analysis, the statistical phenomenological analysis on the left with the standard Jacob-Piran formula for the redshift dependence. And you see that statistically it does pretty well, but the red point is the one that I focused on earlier, the one from gamma ray burst 09, 05, 10. And this red point is much off the line, and as I explained, it's very difficult to imagine a conspiracy that would allow it to become consistent with the rest of the picture. Now, on the right, I show the analogous scheme of analysis done within our toy model with curvature triggered effects. And as I mentioned, this model gives effects which are of the same order of magnitude as the standard Jacob-Piran model, but the onset is lower as more redshift because they are curvature induced. So when the redshift is small, the suppression by curvature is not sufficiently compensated by the premium due to distance. And so you see the onset is weaker, and as you see from the graph on the right, actually one gets a somewhat better picture of comparing the model to the presently available data. And this is basically all that I wanted to say, because the analyses are pretty long and detailed. I spared you the detail. I gave references where all these details, of course, can be found. The bring home message is that well, this data situation is more intriguing now with this new model, but I don't make much of it. I mean, these are just a few data points. The analysis has a number of caveats. I mean, I suggest everybody to monitor the situation. It's intriguing, but chances are, it might go away as more data are accrued. Of course, it would become even more exciting, of course, if more data are accrued consistently with this picture. But right now, my expectation is that, okay, this is on few data points, we are doing pretty well. But as more data are accrued, the situation might fade away. What my main message instead is that these models with curvature triggered effects, which are favored by most theoretical models, and we now show that they provide a phenomenology which is completely competitive with the standard Jacob-Piran formula-inspired phenomenology. These models with curvature triggered effects are not going away. These are going to be new players in the phenomenology of quantum gravity. And with this, I can stop. And time. Thank you.
Let's thank the speaker. And we have a question from Nicholas.
Yes. Hi, Gianni. Happy New Year. Nice talk. Two very short questions. The first question is, if you consider geodesic motions, then you do include curvature there, classical curvature. And then you can get, for instance, Ford has done this, Lenny Ford and myself and John have looked at it. You can arrive at, using geodesics, you can arrive at stochastic effects of curvature. So my question is, did you try to match your momentum model, which I understand is as you said, is a toy model, with such the geodesic approach? In other words, consider the geodesic, which contains the curvature, and then look whether it gives similar effect. That's my first question.
Thank you, Nick. Oh, this is actually allows me to elaborate on my final remarks. We, the consensus among, when, in Europe now we have a cost action that you also take part of, and when we had discussion about these curvature triggered effects, everybody was just discouraged. They said, no, it's not worth looking at it because you get the double suppression by curvature and by the Planck scale. So to answer your question, right now in this first analysis, we just wanted a very simple toy model where we could make clearly the case that these curvature triggered effects are relevant. And now what you suggest, of course, is the next important step. So to now look at existing models where these curvature triggered effects are present, and understand which features are generic, which are model dependent, but I think is a new opportunity for phenomenology to go in that direction. I think one robust feature is that at small redshifts, they will be smaller effects.
Yes, that is true. Even intuitively, you expect that.
Yes, this is a robust, but instead it will be very interesting now to look at your model with Ford, and also there are some models in the loop quantum gravity community with these triggered effects, to see how then in the detail this toy model surely does not capture everything, and of course the phenomenology should look more refined.
It captures some essential things, that you have it proportional to momentum. So the higher the momentum, that's quantum gravity, of course, that's the standard. And do I have time for another very small question, or?
Yes, you do.
As you know, if you consider defects, space-time defects, the real quantum gravity scale could be redshift dependent simply because it depends inversely proportional to the density of defects, because that's the probability with which the particle. So this, of course, changes the Jacobi-Run formula as well. And I was wondering whether this small, this formula, that this curvature effect, of course, these have also the defects. It's also, in a sense, a curvature effect. So that's what I wanted to say, is rather a comment rather than a question, that you could also have generic phenomenologically extra dependence on the redshift, because the Planck scale is effectively a different one than the standard Planck. That's
yes, I agree. Well, you know that you and I have been trying, and others have been trying to, this has been this line of research has been one beautiful result of it, is that the astrophysicists became interested in quantum gravity. One difficult part has been, once Jacob and Piran very brilliantly came up with their formula, and Jacob and Piran are from the astrophysics community. The astrophysics community embraced very strongly this redshift dependence proposed by Jacob and Piran.
Actually, it was actually Sarkisian, Zakharov, and myself that first derive a redshift dependent, but we have missed the time delay. And that is where, so Piran has just corrected us because of the time delay at the propagation, because we ignore that, that's all.
I know the story, but I was emphasizing, yes, you're right.
No. All I wanted to say is that
Jacob was final and was useful anyway.
Yeah.
I think it stuck with the astrophysics community because, of course,
it's at large distances,
and it made a lot of sense to them. And so for people like you and me now, it's a little bit difficult to explain to astrophysicists that there are, however, other possibilities, and it could be the defects that you have been studying for years, and it could be this kind of relativistic curvature effects that I've focused in my talk. So there is really a broader phenomenology than what has been done so far, focusing only on that one formula. I agree totally.
Indeed. Thank you. Very nice.
Right. Thank you. I think there are no more questions.
No, there is a question. Sorry, Sharon. There is a question in the chat.
I don't see.
There is a question in the chat.
I said I have a question.
Okay.
Just a curiosity.
Have multiple hands from Rafael Brown. Okay. Lucas Maldone, could you please either type your question or speak?
Do you hear me? No, I'm speaking. Do you hear me?
Yes.
Yes.
Ah, perfect. Now, just it's more a curiosity, and you probably also answered partially. How much this depends? This kind of effect depend on the particular underlying theory of quantum gravity. I know you used some toy model, but if you want to use some of most famous theory of quantum gravity, I don't know, quantum gravity, string theory, or triangulation, other stuff. How much this kind of effect would be affected by the choice?
Thank you for the question. So really, we have more experience with the previous type of effects, the ones before my talk, basically the ones not triggered by curvature. But that is probably representative of what I'm going to say in general. So once at the phenomenology level, we put in focus those effects. Indeed, this was already in the 1990s by papers that Orgenik, myself, and others wrote. Then, once you bring this to the attention of the community, in some approaches, the problem is that working in these approaches is very difficult. For example, even now, after 20 years, in loop quantum gravity, it's not completely clear whether these effects are present or not. It depends very much on the kind of approximations and simplifications that are needed in those complicated models. But when you do find them, they are not very different from what phenomenologists had envisioned in some sense. In some models, they will not be there. For example, in string theory, in the standard critical string theory, Nick and others have an approach of non-critical string theories where these effects are clearly present. But in the standard critical string theory approach, we assume Poincare invariance from the beginning because you put it by hand in the construction of the theory, then these effects are not present, for example. And in space-time non-commutativity, these effects are often present and they can be computed pretty reliably now after 20 years. In loop quantum gravity, we don't know. So let's say string theory, surely not if you assume from the beginning Poincare invariance by force. Loop quantum gravity, maybe, but when with the arguments that show that it's there, then it's there in the same format. And then in space-time non-commutativity, definitely in some models these effects are present, and they take basically the form that phenomenologists had envisioned. Now, in other approaches like group field theory, it appears that these effects are present. For other approaches, they are still too early and too complicated to know. So to give you a feeling is, it's very important that we get these toy models. So we explain to people that the question really matters. I'm pretty sure now, with these results on the curvature-induced picture, you will see on the theory side more results trying to understand if these effects is present, because there is motivation now. They know, the more formal theorists know that it matters if you find such a result now.
Thank you very much. I knew that in fact in this Nick's model, in these different models, you have this kind of effect because we work together on neutrino oscillation effects coming from this Poincare violation. So, but I didn't know about other theories at all. So thank you very much.